The rungler module has a slightly different history because in traditionally you find in synthesizers these noise generators, and these noise generators often only just have one output that says noise, and maybe they also have a switch that says white or pink or brown or something or red. And sometimes they even have a knob where you can go from white to pink or something. And that's it. And all they do is go shh all the time. I've always found that a bit boring modules myself. But being Dutch and living in the town of The Hague, I was already introduced to this Dutch composer Jan Boerman already long time ago. And Jan Boerman is one of these composers of electronic music that already started to compose in the late 1950s, and is his work is absolutely worthwhile checking out. And he, in the early 60s, he developed this sort of quite interesting idea that if you take at one side a sine wave, and a sine wave is basically the most simple sound phenomenon that there is. A sine wave is a little bit like distilled water, and like distilled water has no taste, a sine wave also has no timbre because it doesn't have any harmonics to give it a timbre. But still, if you take a sip of distilled water, you immediately recognize it as distilled water. So it's a bit debatable whether distilled water has no taste or the taste of distilled water. In the same way, the sine wave has no timbre or it has the timbre of a sine wave. But it is the most singular thing that you can get in sound. And at the opposite side, there is noise. There's pink or white noise. Because in noise, basically, over a span of time, a given span of time, every frequency will be present there at any possible amplitude. And if you spend this time from the beginning of the Big Bang or the creation up to Ragnarok or the end of times, then probably every possible frequency at every possible amplitude will have passed at least once. So it is the signal that sort of compresses all, or not compresses all, but encompasses all. Is that a good word? Encompass? Has everything in it.
Includes.
Includes.
Incorporates.
Yeah. So Boerman thought if noise is sort of like the most complex system, absolute complexity there is, then any sound should be hidden somewhere in noise. And so in his composition techniques, he specifically tried to explore that range that is between a sine wave and noise. So you make a sine wave more complex or you make noise more simple, and then see what you can find there. And well, I like that idea very much for maybe something to make a noise generator more interesting. So that is basically what I tried. If you take this output and you listen to this output, you hear that we have noise. But we can do quite interesting things with this noise. First of all, this noise is actually clocked. So we can change the pitch of the oscillator that clocks the noise.
How can noise be clocked?
That's a very good question. That depends on how you generate the noise. You can either take a very noisy electronic component or a natural noisy sound as a starting point. But you can also generate noise with sort of digital techniques with an algorithm. And then that algorithm needs to iterate to constantly produce new values. And the rate of iteration is basically clocking the noise. So now you hear that every now and then it changes to another value. So now we clock the iteration of the algorithm at a very slow rate. And if I speed this up, driven by a VCO, and then of course I have to turn the right knob. We start to produce more and more changes in the output signal. And if you do it faster enough, we perceive it as noise. Basically, it is a random number generator. It's a Monte Carlo machine, the Monte Carlo algorithm as they call it. But I made a couple of adaptations to this algorithm to be able to create shorter patterns, because noise is basically a pattern that ideally never repeats, or only repeats after such a long time that we are not aware of when it repeats. But it's quite interesting to sort of make it shorter in time, so that it actually the sequence of numbers that is generated repeats after an interval that we can actually perceive. And I can actually already do that like this. That now we have a series of numbers that repeats exactly after a certain amount of time, and that you hear. That is the repetition, so that is the length of the sequence. Then it might also be interesting to make this sequence, because now it's something like 2,000 numbers, to make it even shorter, which I can do like this, and now it becomes a really short number. I can actually change this pattern in this way. And again, now you tick, all the changes. But when it changes, it only changes 2 or 3 numbers in the whole sequence, which is 32 numbers. So it's just minute changes that you hear. I can also make these changes a bit more drastic by changing more numbers at the same time, which I do like this. Okay. So that is more or less the sort of extra options that I added to the standard random noise generator to make it a bit more interesting. And I must say that I already discovered this kind of techniques a very long time ago, and I've been using them for quite a while. And it's based on a specific kind of technique.
Rob, the sparse, dense, random switch, how is that limiting the bandwidth of the data? Is it just like a filter on it, or?
No. It is basically it is a sort of an algorithm that is based on what they call a shift register. And the idea of a shift register is that it is like a very simple digital delay. But it is so simple, it's not 24-bit or 8-bit, or it's only 1 bit. So the value that can go into this delay can only be on or off. And it is also of a very short length, 16 or 32 memory locations. But then the interesting thing about these shift registers is that you can basically, it has a data input and it has a clock input. And the moment when it receives a pulse on the clock input, it looks, is the data input a 0 or a 1? And then it shifts in that 0 or 1 into basically the pipe of the memory locations. And every other 0 or 1 that is already in the memory is pushed up 1 position further in the pipe. If you would like take 24 of this in parallel, you would actually have a 24-bit resolution digital delay, but only with a super short delay time. But the thing with the 1 bit is that because it is a circuit, a technique that is used in every computer, in your phones, in your USB, because it is a technique to convert a parallel signal that contains of several bits into a serial stream of bits, or to convert a serial stream of bits back into a parallel sets of bits. Because every memory location in this shift register has its own physical output on the chip. So basically what you do is you clock in a pattern of zeros and ones, and that shifts over all the outputs. And then the trick, what you do, is that if you want to make a random number generator, you can actually take 2 or more of these outputs, combine them in a strange way, for instance by multiplying them, 1-bit multiplications, and actually feed the result back into the data input. And then if you use the right outputs, then you can actually create sequences of numbers where the maximum amount of numbers that are possible, for instance, within 8 or 16 bits, will all pass once, but in a random order. And if they have all passed once, then it will actually repeat that again. And that is the common way that computers use to generate randomness. And that basically, if you convert that to a voltage, will basically give you the noise. And the idea is that the longer this delay line basically is, and the faster you clock it, the more possible numbers can pass. And so maybe if you like take it like 32 bits and you clock it at maybe 100 kilohertz, it may actually take a couple of days before the whole thing repeats. And then for all purposes it's noise or randomness. But it's not really random. So if you look into the technical literature, they actually call them pseudo-random generations, because within a short span of time it appears to generate random numbers, but you can actually determine what will be the next number if you would calculate the algorithm on paper, because that will always be the case. And it repeats after a certain amount. So for statistical purposes, it's not a very good method to use. For real statistical purposes, you would need more random techniques. But all these synthesizers from the 80s and 90s, analog synthesizers, they had this little chip, 8 pins, that was the noise generator, and what that just contained this thing and was internally clocked with a clock of 100 kilohertz, and noise came out. So, but then if you make it with discrete components, you can manipulate the schematic and do more stuff with it. So my idea was basically to have a relatively short delay, maybe only 8 or 16 bits. And then what you do is you do not sort of use the logic levels and do a logic operation to feed it back, but you just add a little digital to analog converter on a couple of these bits to create different voltage levels, and then with these voltage levels you actually modulate the oscillator that is clocking the thing. So up to now we have only just been clocking it, we didn't apply any feedback or whatever. So if we go back to this sound, we actually listen to the on-off pulse that comes out. I can also listen to the voltage levels that I created by adding a little digital to analog converter on these output bits, which more or less sounds the same, but it sounds a bit smoother. Now I can actually feed this back into the pitch of the clocking oscillator that provides the noise clock. But it becomes a bit more interesting if you use this signal to drive the pitch of an oscillator, for instance. So if I take this step signal and I feed it into the pitch input of an oscillator and I listen to the output of the oscillator, I will just give it a sine wave. Then can sort of cluster the sounds. Up to a slightly more extreme point. And you see that now I'm in a mode where it actually constantly repeats. But I can also just now and then sort of, and that's the trick of this thing and why I call it a rungler, you can now and then sort of give the thing a kick to do something else. Sorry?
Is the rungler, is it possible to listen to the modulated signal from it on its raw state rather than it driving the oscillator?
Yeah, but then you only hear the clicks when it changes. Now you can actually hear the changes produced by the voltage steps. or total randomness. Okay. So basically the idea is that instead of just only having this shh, you can actually produce modulation signals that you can use to modulate other things. So now I just only modulated the sine wave oscillator, and you can already hear that at different modulation rates you get completely different kind of effects. And so if you do it at a very slow rate, you really sort of have the idea that you hear notes. So if I sort of, these are all singular, unrelated notes. But then if I speed it up a bit, you come into this area where basically all this granular stuff takes place, where it seems like individual notes that actually are not sounding at the same time seem to sort of melt into a more chord-like effect.
Is that because of the values you're sending back into the, the three sort of setting states?
Well, basically, I'm just sort of using it now almost like a step sequencer.
Right.
So you have steps that follow each other, but if you do that at a certain rate, the mind comes to the point where it goes between sort of singular events to an audio waveform, and somewhere halfway in between there is this point where it's sort of the point if you have a movie. You know, if you have 5 frames a second, you can really book. It's like individual pictures that come by. If it's 25 frames a second, it's a flowing thing. But if you do it like 12 frames a second, you get this sort of effect. It looks like a movement, but you also get the idea that you can sort of single out single pictures from it. So single notes. Then if you go faster, it becomes like one wave.
Is it not like a form of wave shaping, using a noise signal to clock?
Yeah, it's a in essence it's a technique that stands all by itself, but used in certain conditions it gets the aspects of wave shaping or the aspects of sequencing or something else. So it is something that, well, actually, if you know the music of Jan Boerman and some of his colleagues, then you probably already recognized all these little sine wave granular kind of things that you will also find, which actually they did by making lots of tape recordings of sine waves at different pitches, then, for instance, cutting the tape all in small pieces, going all together and randomly cut all the pieces of tape back together again and then run it through the tape machine. Yeah. Which was 1962 or something, you know. So now we have a little device that can do that. So basically the rungler consists of a clock generator, a clock oscillator, which is the same kind of oscillator that you will find as the LFO-A in the triple LFO section. This also has its direct output, so we can listen to that output, and then basically you hear the same signal that you hear in the other. there is another oscillator, and this other oscillator basically sort of manipulates the data that goes into that shift register. But that also has a separate output as a triangle wave, and that can also sort of use the same kind of modulations that you find here. So if we listen to this one, we can actually use this fluctuation that we had on the other one. But we can also, because this shift register, or the rungler as I call it these days, is working in the back, I can feedback the signals and create all sorts of clicky kind of signals. That sounds a bit different than normal clicks because they actually are based on this sine wave. So if I close these modulations, you see that here we have the same one here, so I can do it like this, do it very extreme. I can also use the noise signal. And that way make a very unstable sine wave. And actually go from that sine wave to that noisy kind of territory. And make all sorts of interesting combinations with the knobs to create something that is a bit different than what the standard noise generator would produce.